Well, now we're going to state when a relative minimum or a relative maximum of a function will give us a tangent line that actually is horizontal. And really all that we're going to show is that if the function is defined on a closed and bounded interval, and if you take an internal point, not the end point, not the A or the B, but if the maximum happens to occur at an internal point, then it's going to be the case where the tangent line at this point, say x naught, will be horizontal. Or the slope of the function at that point will equal 0. So here's the statement of the theorem. Theorem 4.6. If f is defined on a closed bounded interval from a to b and it goes into R, if it has either a relative minimum or a relative maximum at x naught, which is strictly in between a and b, it's not one of the endpoints, and if f of f is differentiable at that point x naught, then f prime of x, you could say that f is differentiable at x naught, obviously, and the derivative is 0. So it has a horizontal tangent line. I've got just about all of the proof already written out. Now, we're going to assume that f has a relative maximum. The proof for a relative minimum would be virtually identical. Only a couple of characters would change in the proof. So we'll prove it just for the case where f has a relative maximum at x0. Let delta be a positive number. Let it be such that this neighborhood, this delta neighborhood, remind you again, that's x naught minus delta to x naught plus delta, that interval, that's all that is. Those two things are equal, such that this neighborhood is completely contained inside of AB. And I know you remember how we can assume that's true. We have an open interval from A to B. At any point, it doesn't matter how close I get to A or B, for purposes of this picture, I'm going to not make it too close. That's my x naught. All I need to do is take the, say, half of the distance from x naught to A, or half of the distance from x naught to B, whichever is smaller, and draw an epsilon window around it. That's all this little neighborhood is. The delta, I called it an epsilon, a delta neighborhood around x naught. Okay, so that neighborhood is completely contained inside AB, the interval. And f of x is less than or equal to f of x naught for all x in that neighborhood. Well, we can do this because f of x naught is a relative maximum. So there's some little window around x naught where this is the maximum value. Okay, well, if we let x in be a sequence, and notice where we're taking this sequence. We're taking this sequence from numbers that are to the left of x naught. So we're taking the sequence over here that converges to x naught. So we know that f of x is increasing as we get up to x naught. Okay, and we're going to choose that such that the sequence converges to x naught. Since f is differentiable at x naught, we know by either the definition or the theorem that followed, it's differentiable there. This sequence, f of xn minus f of x naught over xn minus x naught, converges to the derivative of the function at x naught. And what do we know? Well, what I mentioned earlier, since x naught is f has a relative max at x naught, it could look something like this. Didn't make that very smooth at the top. we know that all the xn's are less than or equal to f of x naught. And what does that imply? That implies every number in here, since xn never equals x naught, every number in here is going to be a positive number, which means that the limit is going to be greater than or equal to 0. Remember, you can have a sequence of positive numbers that still converges to 0, which is not a positive number. So we know that the derivative is greater than or equal to 0. Now, I'm going to do the same thing with the sequence that starts in this region and converges to x naught. So let's let yn be a sequence on the right-hand side of x naught, between x naught and x naught plus delta, that converges to x naught. By the same reasoning above for the sequence xn's, we know that this sequence converges also to f prime of x naught, and in this case, f prime of x naught is less than or equal to 0. Every term in here would be strictly less than 0, so it's converging to a number that is less than or equal to 0. So I think one more line and we're done. Since, let's see, f prime of x naught is less than or equal to 0 from here, and it's greater than or equal to 0 as well, which I can write like this, we see that f prime of x is equal to 0. And that completes the proof. I'll leave it to you to convince yourself that this is full of negative terms and this is full of only positive terms. But it's basically because when xn is to the left of x naught, this is a negative number, and so is this, because it's an increasing function. And it's decreasing on the other side. It's increasing up to the relative min. It's decreasing to the right of the to the relative maximum. And therefore, all of these are going to be negative terms.